All right, so what we're going to do is talk a little bit about what an aircrew trainer is. That was pretty much my bio. I'm going to go ahead and talk about the things we can cover today. We're going to start with just what is an Apache Longbow helicopter and what can it do. Then we're going to go into what is an aircrew trainer and what makes up an aircrew trainer. We're going to break that down and look at some components of an aircrew trainer. Then we'll get to this technical aspect of what we call a distributed computing system. And there are lots of distributed computing systems, and our aircrew trainer is one of those. And hopefully at the end we'll have some time for some questions. So to start, there's the helicopter and what it looks like. It's an Apache Longbow helicopter. Some things about it. The AH, if you didn't know, stands for attack helicopter. The main primary role is anti-tank, kind of close ground support for the Army. The Apache is the name, and actually all U.S. Army helicopters have a Native American tribe designation. There's a Chinook, like the Huey helicopters from Vietnam are actually named in Iroquois. Little known fact about Army helicopters. And then the D in the Longbow refers to this model that can carry this, what's called the fire control radar up on the top of the helicopter. The previous Alpha models, the A models, did not have a radar on them. There's two crew members. The guy sitting in the back is the pilot. His main job is to fly the aircraft around. And in front is what's called a co-pilot gunner, or CPG, whose main task is to work the weapon systems. And to look at some of those weapon systems, what you see on the outboard pylons are rocket pods, and there's a nice picture of an Apache firing some rockets. These pretty much fly just pretty straight, so you got to work the aircraft to get these to fly in the right direction, but the pylons can move up and down a little bit. For accurate targeting, there's this Hellfire missile that's used mostly for large targets, and these can be laser or radar guided. And the other main weapon is there's a gun down here. And so we got all these weapons. You got rockets, you got Hellfires, and you have the gun. So how do you aim these things around? So we'll look at some of the sights. We talked about this radar. The radar can find targets and locate targets, and these rockets, Hellfires, and gun can also can be slaved to find these targets. Both crew members wear this crazy helmet that's got a lot on it. The big part you see on the right is called the IHADS, or the Helmet Display Sight System, and it embeds video right into the crew member's eye. And it's also attached to a helmet tracker, so as he moves his head around, he can see the video that's showing in his eye. And then up here is the main, like, the eyes of the helicopter. It's called the TADS and the PNVS, the Target Acquisition and Designation System, and then there's the Pilot Night Vision System. And this next picture, you can see that really up close. So there it is, right in the front. This first part, the TADS, on the left you have a forward-looking infrared image that's actually on the right. That's the right camera, and on the left is a day TV monochrome camera. And then on the top is a smaller thing that is attached to where the pilot's head is looking. So as the pilot looks around with his head, this sensor moves around and gives him an image as if he's looking around with his head in night vision. So, and then, of course, there's so many more complex systems. There's fuel systems, navigation, how the landing gear works, emergency systems, so many different systems. And so the question becomes, how can crews be trained to operate these things safely and efficiently? Ideally, if there was unlimited resources, all these crews would train in the aircraft and they'd have instructors. But that just becomes cost. The cost goes through the roof, and it's also dangerous for these pilots to train in the real aircraft. It's a very difficult aircraft. So the answer is that we have to simulate all of these systems in the most realistic real-world setting as possible. And that provides the safest and the most reliable and efficient training. So here's a picture of the LCT that I work on. It looks just like the real helicopter. What you see out here is a simulated out-the-window image generated by an image generator dedicated to making that image in the visual scene. Some other parts of it, all the displays need to be simulated. On the right, you see there's actually a fuel flow display. On the left is more of an aircraft display. So every display that could ever come up in the aircraft needs to be simulated. There's the control sticks. The main stick in a helicopter is called a cyclic, and on the second from the left is the collective, and there's the power levers on the left. One thing about that is these sticks need to have the right force feedback for all the flight conditions, so that as these just like the hydraulic pressure in the aircraft feeds back on the pilot's feeling of the stick has to be exactly replicated in the simulation so that it feels real to them. And then, of course, every knob, every switch on the right, you see what are called standby instruments that are analog gauges that are on the aircraft, so those have to perform correctly. There is a motion seat. This simulator doesn't rotate around in 360 degrees, but it has a motion seat that can move. The seat can move forward, the back can move up and down. It can give you some kind of shaking, and it gives the crew a feeling of what it's like to land on the ground. And as you pitch forward, as the seat moves, it doesn't really feel like negative G, but it does give you enough of a feeling to give you some feeling about how you're flying. And both crew members have that. This is where we do our magnetic head tracking, so we could track the pilot's and the co-pilot's head movements. Here's where the FLIR image comes up. So we remember that sensor from the front. All that video has to be simulated in a true IR sense. And things you wouldn't even think about, like just the way that structure is around the pilot's and the co-pilot's head. They need to get used to where these obstructions are so that they know where to move their head and how to find things in their image. And then there's an instructor-operator station where the instructor can sit and communicate with the pilots, set up missions, and so forth. So that's some things. Let's look at even more. So here's just a nice picture of an Apache doing its thing. But as you look around, you can think, what can we see in this picture that would need to be simulated for training purposes? There's things you might not ever think of. For example, the position and the orientation. All the scenarios correlate to real-world locations. So if there's a tree in that lake in the real world at that GPS location, that's what we need to have in the simulator so that they know exactly where they are. Also, just the weights and balances. As these weapons go out, the aircraft flies very differently when there's no weapons or when there are weapons. So with the way the fuel transfers, all those things need to be simulated in the flight dynamics. Loads of environmental factors, like the time of day. We have to simulate all times of day, from midnight to dawn, winds, all the way to where the sun and the moon is at the time of the day for that date, so that if they're flying a practice mission, they know where the sun is for their routes. A lot of infrared effects, like there's an effect called thermal crossover that happens with infrared images, where things look good in day, things look good at night, but there's a certain time when the variation between the image starts washing out a little bit, and they have to train in those situations. From clouds, almost everything you can imagine. From obstacles, the helicopter pilots don't like power lines very much. They really worry about those kinds of things. So that's a big deal. All the way from like the slope of that terrain would need to be simulated so they could practice sloped landings. And here you see the trees in the back, so we have to worry about line of sight occlusions to other team members or other players, so that they can't communicate with radio if they don't have radio line of sight to other members, and how to deal with all of that. All the way to the rotor wash effects. Something about rotor wash that was pretty interesting that needed to get added to the trainer that wasn't there previously is the brownout condition. What a brownout is that happens a lot in desert situations, is as you start coming down to land the aircraft, everything's going fine, you see what's out in front of you, and then as you start getting close to the sand starts recirculating into your downwash, and the whole image just completely blanks out. And now you're trying to land this aircraft, you're close to the ground, and you can't see anything in your image. And so they had to train that about how to deal with that situation and how to perform it safely. So this is a water-based rotor wash, so we have to make sure that when they start taking off, that rotor wash effect is correct. Something that's also in there that the instructor can do that's kind of mean is insert all sorts of malfunctions, just the worst things you can think of. Engine fires, your video just goes away, your hydraulic pressure can go low, and whatever you can think of. You go to fire your weapon and your weapon doesn't fire. What do? And they just inject these things while they're training and train the proper procedures to deal with all of that. Almost anything you can think of that can go wrong. So now we'll get to, so how do we get all this stuff to work in software? Here's a little, just a sample block diagram of a software-hardware communication architecture. So this green box, all the green boxes will represent hardware. Somewhere in there, there's a magnetic imaging system that's on the top of the crew station that determines exactly where this crew member's head is looking. So there's all that hardware. And then the yellow objects are PCs. There's PCs that are just dedicated to communicating with that hardware. And then there's an interface. There's an interface between the software PC and the hardware itself. So that's one of the interface types. Another example is the motion seat. So you got all the hardware that goes into actually making the motion seat work, and it too has a PC dedicated just to talk to that. So that's represented here. Some computing systems don't have hardware connected to them. So there's a threat environment. It's just a software program that's just out there to drive threats. It has behaviors in there. It can drive the bad guys. It can drive your cooperative players. And the instructor can control these in the situation, in the scenario. And again, like the instructor operator station is another application that's out there. And we talked about all the switches and the knobs, and all that hardware needs to come in somehow so that, like this, for example, is a radio panel. All those volumes for the radios and those knobs actually go up and down to determine which radio is selected, and all that needs to get into the system. And that feeds into a PC that groups all those together and gets all these, whether they're analog, like voltages for knobs, or discrete switches for up and down, on and off, and puts those out there. Another major system, this isn't quite hardware, but there's a major system that just draws the images. It draws the images out the window, it draws all the TV camera images, and it draws the infrared images. So this also has a software interface. So the question becomes, so now you have all these things out there, and what do we have that can hold all these pieces together? And this is the main thing that I work on, is the main host software. So you can think of all these yellow boxes as separate hardware computers, separate software programs. And now all these things need to talk to one another appropriately. And so there's all sorts of interfaces between the main host software and the PCs that talk to the different hardware components. The head tracker just operates on a kind of a pretty basic serial interface, just like your printer on your PC. Gives information like where the pilot's head is looking, things that we have to tell it. We have to tell it what kind of mode it's in. So that's that interface. The motion seat, we have to tell it what the flight condition is and how we want it to move, and if there's a malfunction that's called droop stop, that where the rotor gets out of sequence and it makes the helicopter shake. So when that happens, we have to get that motion seat to shake around. The threat environment communicates, we can talk a little bit about this interface, communicates over what's called a DIS interface, which is a common, DIS stands for Distributed Interactive Simulation. And it's a common interface that can be talked so that our software can not only talk to our threat environment, but any threat environment. And what that provides is, as we're talking to it, telling the threat environment where we are, so that the threats can interact with us, it's telling us where it is, where all the threats are. And what that provides is that if you take two of these trainers, and they're both talking over the DIS interface, Now 2 of these trainers can now be linked, just like a kind of an online computer game. So now two completely different trainers can talk to one another and see each other. The iOS has an interface. It tells us things like what scenario are we on, environmental conditions, the malfunctions come over this interface. And the knobs and switches all come over. This interface is also common. It's called a SIGI interface, CIGI. Stands for Common Image Generator Interface. And it's a common interface that can be used to interface into any image generator. Sends things like, where are we looking? Where is this threat? This threat has different articulations, and draw this animation. Actually, for our software, everything is synced off the IG so that the video is as accurate as possible. So it's sending us constant updates all the time. And the way our software works is it works in what you see is this black bar is like a frame rate. Our software frames it at a 60 hertz rate, essentially. So 60 times a second, our software must process. And you can see at the left-hand side, we're pulling in the head tracker interface. We're pulling in the knobs and switches. All the way through all the different components. And we split up our software so that certain components, we call them, of software are only have to deal with certain things. So on the left, you see a component just dedicated to the head tracker. And you see a component just dedicated to the threats. And as this, as this thing's framing, we can communicate within, think of the main host software block as one big software program. And so, for example, let's say we're flying around. On the right, you see the flight model. It's processing the flight model. That data is coming over to the visual, which is then talking to the image generator interface so that we know where we're looking. Same with the threat interface, so that goes out to the image generator, so we know where to place those threats in the scene. So all these are talking, you can think of all the yellow boxes and our main host software as separate programs. And so the question becomes, in a technical sense, is this a distributed system? You can see there's PCs everywhere, and they're all doing their thing, and they're all talking to one another. And you'd think that it is a distributed system. And in some sense it is. It's distributed all over the place. But there's a more technical definition of what a distributed system is. When I click this, some of these interfaces are going to go away just for simplicity. But think of all these things talking. And we're all talking at a 60 hertz frame. Well, there's a lot of software running on this processor. There's everything you see there, plus all the malfunction processing. We rehost the aircraft software, so that has to run and talk. And we don't have the ability to process all of this stuff at 60 frames a second without overframing. So to make this a distributed system, what we do, so if I click here, we're actually going to split up this. Now you have one executable, one software program, but now it's distributed amongst 3 different PCs. So you just have one software program, and it's spread out. So now each of these PCs can frame together. So on the left-hand side, you see this, like if the switches are talking to the head tracker, they just talk internally. But if you're on a different PC out of these 3 blocks, then those talk over a network. And so now you've split the workload of this one program. Even though it's still one program, you split it amongst 3 different PCs. Ours actually has 7. And they're just off-the-shelf Linux processors that can all process together. And the fancy part of it is that with this one program, with just changing a few configuration files, you can move these components around to different processors and try to optimize the processing. And so this now is the definition of what is a distributed computing system. It's one program running on a bunch of different PCs, all to perform one task. Another example of a distributed computing system is the way Google works, as I understand it, that there's not just one big computer that has all of Google on it. There's lots of simple computers that share the workload, just like this goes. And that's just about it. Are there any questions about any part? Yes, sir.
Just quickly, the magnetic head.
Right.
And you mentioned the magnetic imaging system. inside the cockpit for a moment, how is there a magnetic field generated that
Right.
interfaces with the
Right. There's a box that's. Let me repeat the question. It's how does that magnetic head tracker work? Is there a magnetic field generated, and how does it know where the pilot's head is? And sure enough, there's a box that sits on top, and it's some other software and hardware that we get. That's main job is to do this. And it sits up on top of the cruise station, and it generates a magnetic field. And we have to account for all that metal and all that other stuff in there because we get anomalies around those areas. And once you map all that out, then you can get decent direction. But there are problems like when the crew puts their head way over to the side, we get some kind of anomalies. But that is how it works. Yes?
How good is the image quality on your, is it very realistic or a little?
It is pretty realistic. One thing that a lot of people have when they see it, they're a little bit surprised that it doesn't. Some of the video games you might see on your platform might have actually more polygons, more textures drawn than you'd actually see in our scenario. The other thing that we have to deal with is we have to deal with the size, so we have big projectors that dilute the image a little bit. And we also have just the size of the database. Like, for example, like in a computer game, you have certain little places that the game is taking place on. Well, for this one, you need a whole. This actual trainer is being sold for the Kuwaiti Air Force, and they need a whole gaming area around their whole, whatever theater they need to operate in. So there's a big pull there, but it does look very realistic. And then there's also the not only the out the window, but the infrared image. There's a lot of worries about the way the infrared image looks inaccurately. Yes?
How long does a pilot or a gunner train in this before they actually go out into the actual academy?
Yeah, you know what? I'm not too sure. They go through loads of ground school before they even get into this trainer, just book learning about just how everything works, and then loads of time in the trainer, and then there's some cooperative flight where they have an instructor with them. And then all the way through live weapons fire before they ever get actually certified, combat certified. Not sure how long it takes, but it's a big deal. It takes a long time. Yes, sir.
If I heard you right, you said something about 60 frames per second.
That's right.
What does that buy you that 30 frames per second doesn't give, and why can't I get that in my local movie house?
It's true. It's true. One main reason for the 60 frames a second is the rehosted aircraft software also runs at 60 frames a second, or 50 frames per second. So that's one main reason for the frame rate is to keep sync with the aircraft software. Another main reason is just the software requirement. Like a major issue is what we call transport delay. And it's the issue of no matter how accurate it is, there needs to be a certain number of milliseconds, I think our requirement's 110 milliseconds, between the time they hit that stick and the visual moves. So all those things need to frame in time between, all right, I got the stick input. What does that mean for my equations of motion and my fuel? And what does that mean for my orientation and then coming back around? So a lot of it's not necessarily the image quality, because I think, for 24 frames per second, it kind of looks pretty smooth, but it's the quickness of that real feeling. So, because I've heard stories that if that transport delay, if you have the most accurate flight model that you can have, but if that transport delay is 20, 30, 40 milliseconds off, the pilots will get sick in there because they're used to the stick. When they move that stick, they're used to seeing a certain input, and if that's off a little bit, they get these guys that can fly incredible missions start getting seasick in there because it's not what they're used to. Those are the main reasons. Any other questions? All right, I guess that's it. All right, thank you.